All right, one final thing to comment on here. Basically, this dot convention reference is just from the textbook. It's from the Eulaby textbook. I just broke it down and put it into a slide horizontally so that you could have it easily to reference in case you need it. But it's important to note that they're looking at things in the time domain here. Basically, they're saying that the voltage between these two terminals is the mutual inductance, well, negative the mutual inductance, multiplied by the rate of change of the current, which is true, but we're not solving circuits in this class in the time domain very frequently. We've been working in the phasor domain, especially in Module 1. We were looking at the stuff in the phasor domain. Same with Module 3. We're not looking at the time domain and solving these, as differential equations. Instead, we're putting them into phasor form. And so when we look at these circuits, we're not going to be seeing these voltages in terms of the mutual inductance and the rate of change of the current, but instead we're going to see something more like the voltage here would be j omega times the mutual inductance, right? That would be the impedance of my mutual inductance multiplied by the current that induced it, right? Using just Ohm's law, right? I times Z gives me V. And so that's what we're going to see moving forward. So it's important to keep that in mind. And so let's just jump into this example here. So what we're looking at here is we basically had a mutual inductance M. We had an inductance L1 and an inductance L2. This is from the Satiku textbook, just an example problem that I'm going to solve. Of course, we had a capacitor C, a resistor R, and some source V in. And they've already put it into the phasor domain for us. Okay, they basically provided it this way. So they're assuming that we already know that this circuit goes, into a phasor domain circuit where this is some impedance, minus J4 ohms. This is some impedance of this inductor. But of course, we don't want to draw it this way because then the dot convention is going to disappear. But this is some impedance J5 ohms. We're going to have some other contribution from the dot convention, etc. But they're basically giving it to us in phasor form already, okay? So what we need to do is we need to take the mutual inductance and incorporate it into our circuit. And the question is, how do we do that? So what we're going to do, well, first of all, what is this circuit even asking us to do? It says calculate the phasor currents I1 and I2. So it basically wants us to find I1 and I2 in this circuit, okay? And I am warning you now, do not try to solve this circuit as if the mutual inductance is not there, because if you do that, you will get everything very wrong and you will lose lots of points on the exam, okay? Because the mutual inductance is there and it does affect the circuit greatly. You'll see that in LT Spice, and we're going to see it here. We're going to see how it affects the circuit. So what it is that we're going to do is, so we're going to just write this here. I have an impedance, J5, for this first inductor, but I need to account, remember, I've got a current I2 that's flowing in this second inductor. I need to account for those flux lines that I know are coming out of L2 and basically linking L2 to L1, and I need to account for the flux lines that are linking L1 to L2, etc. And I know that this current induces a current flowing in this circuit, and vice versa. And I know the mutual inductance by the value M. Here it's given already as J omega M, which is J3 ohms. And so how we account for that, again, is we use the dot convention to determine what is the voltage that's going to be induced by the dots and by the mutual inductance. So for this circuit, since I'm drawing the loop on the left-hand side first, and I know that it's the current I2, right, through this inductor that induces a current in this inductor here, let's take a look at that one first. How are we going to account for that? So I2 is flowing out of the dotted terminal here, right, out of the dotted terminal. Remember I said a current flowing out of the dotted terminal on one side forces a current into the dotted terminal on the other side, okay? So we need to incorporate a voltage source, an induced voltage source on the other side here. Let's just draw it as a dependent source. And it's going to need to force a current because this current's flowing out of the dot here, that source needs to force a current into the dot here. So what polarity of voltage source is going to force a current to flow this way? That would be a voltage source that has a plus here and a minus here, right? That would force a current to flow this way in this circuit, okay? And that's exactly what we need. And what is the size of that that voltage source? It's basically going to be my mutual inductance, J3, multiplied by the current that induced it. So it's going to be J3 times I2. And that is how I would account for this first loop, okay? So let me write I1 here. And I've basically taken the mutual inductance out of the equation. Or I've incorporated it into the loop, and now I don't need to draw it here anymore, okay? So now let's do the second loop. Of course, I've got an impedance of this inductor, J6. We also know that we have a resistor of 12 ohms, okay? And lastly, we're going to have another dependent voltage source here, but we need to take into account the current flowing in I1 now, because that's the current that induces this voltage. So I1 is flowing into the dotted terminal of L1, which is going to force a current out of the dotted terminal of L2, okay? And so what current or what voltage polarity would force a current up through this inductor? That's going to be a plus here and a minus here. And again, it's the mutual inductance multiplied by the current that induced that voltage, okay? And so this right here is my circuit that I now need to set up the equation for and solve using basic mesh analysis. This is very straightforward from this point. I think that the biggest challenge is going to be getting to this point and confidently getting to this point. If you have any questions about how I drew the polarities of these dependent sources, note that it's just the mutual inductance multiplied by the current that induced that voltage on both sides. So on the left-hand side where L1 is, right, this is basically my L1, the impedance of L1. This is the impedance of L2. On the L1 side, I have a current induced or a voltage induced, both, you can say either or, induced by the mutual inductance and by I2, which is flowing on the other side. And on this side, I have a voltage induced by the mutual inductance and the current flowing on this side, okay? That's the way that this magnetic coupling works. And from here, again, it's basic mesh analysis. We just set up our pluses and our minuses across our impedances. We've got some voltage sources in there, and we can just throw these two equations, two unknowns together, and very easily solve for these currents. So I'm going to go ahead and end this video. I know it's gotten a little bit long. In the next video, we'll wrap up the mesh analysis, and then we'll move on to, I think I have another example here. Let's see. Yeah, so we're going to do a couple of examples, just go through a few so that we can get a feel for how to represent these circuits and how to solve them. And yeah, hopefully we'll piece together our understanding of these concepts. All right, so I'm going to end this video here, and we'll see you guys in the next one.